Good evening. My name is Deb Marr, and I'm a professor in the Department of Biology at Indiana University, South Bend. I'm serving as tonight's moderator for this talk. Just for your information, so the exits and restrooms are just straight back. The Our Universe Revealed lecture series includes talks in the sciences and the cross-section between science and the arts, so STEAM for everyone. We feature research and creative work that's being done in our region, and it's an opportunity to be curious about ourselves, our world, and the universe. This is a partnership between the St. Joseph County Public Library, Indiana University South Bend, and the University of Notre Dame. I want to particularly thank the speakers tonight, so Boldazar Yanko and also Adam Jaffe. So the Nobel Prizes are announced the first week in October. And then we say, who in this region has expertise in this area who can talk about it? And I really appreciate your willingness to put together and share your expertise with us. And so I really thank you for being here. So just a little bit about the Nobel Prizes. So what I'll do is I'll give a little bit of background on the Nobel Prizes, a little bit of background on our speakers, and then I'm going to turn it over. First, we'll think about the Physics Prize, then the Chemistry Prize, and then we'll have time for questions. So Alfred Nobel was a Swedish chemist and an engineer, so near and dear to his heart were actually the chemistry Nobel Prizes. But in 1901, when he died, he set aside money to fund 5 of these Nobel Prizes, so physics, chemistry, medicine, literature, and peace. And they began awarding them in 1901. And then in 1969, they added a Nobel Prize in economics. And so the Nobel Prize is awarded to those whose work has conferred the greatest benefit to mankind. So from 1901 through 2025, there's been 633 Nobel Prizes that have been awarded to 990 individuals and 28 organizations. There are rules, really strict rules. One is that the prize cannot be shared among more than 3 people. And tonight, the Nobel Prize in Physics is awarded to 3 people, and the prize in chemistry was also awarded to 3 people. The laureates receive a gold medal and a diploma, and then about $1 million US dollars. And the ceremony will be December 10th in Stockholm, Sweden. This year was particularly competitive. So actually applications were up 20% this year compared to last year. So there were over 300, so 338 candidates this year. There were 286 candidates last year. So this year was particularly competitive. So for our speakers, Boldazar Yanko is a professor of physics at the University of Notre Dame. He earned his bachelor's degree in Hungary and a PhD at Cornell University. He's the recipient of the Alfred P. Sloan Foundation Fellow. This is awarded to researchers whose creativity and innovation is considered unique, and they will be a leader in the field. So Professor Yanko leads the condensed matter theory group at University of Notre Dame, and he collaborates with the nanoscale interdisciplinary research team. This brings together theoretical and experimental researchers from 4 institutions, so Notre Dame, the Argonne National Lab, University of Illinois in Chicago, and Duke University. And by combining this expertise in different areas, they are documenting new behavior in electronic systems, and this is leading to major developments in spintronics, nanoscale superconductivity, and magnetism. It's a fundamentally different way of thinking about electronics, and in many ways kind of embodies the Nobel work that's being talked about tonight, in that they're looking at a system from different perspectives. Adam Jaffe, he'll be talking about the Chemistry Prize. He earned a bachelor's degree in chemistry at Princeton University, a PhD in inorganic chemistry at Stanford University, and then was a postdoctoral fellow at University of California, Berkeley. He started at University of Notre Dame in 21, and he is a Scialog Fellow. This is awarded to scientists who are addressing scientific challenges of global significance, and then also an NSF Career Award. The research in Jaffe's group combines organic compounds with inorganic solids to develop hybrid materials that have unique properties, electronic properties that can be used for new uses. And so this hybrid organic inorganic approach contributes to our understanding of electronic conductivity and applications in clean energy. And all of this connects to the Chemistry Prize this year. So I'm going to turn it over to Professor Janko to lead us off.
Well, good evening, everyone. Thank you so much for joining us tonight. So let me just tell you a few words about the Physics Nobel Prize this year. The awardees are John Clark from UC Berkeley, Michel Devoret. He actually has a joint position between Yale and UC Santa Barbara, and John Martinez, who is now at another University of California campus, also at Santa Barbara. As Deb was mentioning, I did my PhD at Cornell. In fact, I worked on what Michel decided to call the Cooper pair box. I'll tell you more about it pretty soon. He and his group took it at a completely different level later on. John Clark is an expert in superconducting quantum interference devices. By the way, he was the advisor. Michel was the postdoctoral associate, and John, believe it or not, despite how old he looks, he was the graduate student when they did the work. We worked on what is called 1 over F noise. I don't have time to get into it, but John is a world expert on that, so it was our pleasure to interact with him, and of course with Michel. And currently, I'm leading a team that works on superconducting electronic devices. By the way, I have several of these here. They are on loan from MIT Lincoln Lab. I'm happy to show them to you. I'm hesitating to pass them around because if they disappear, I'm in deep trouble. In a very classical state of deep trouble. Okay, here's a list I want to start with. This is a list of Nobel Prizes that were awarded to work related to superconductivity and superfluidity. They are not the same, but they are closely related. From this list, I would like to spend some time on the work of then a graduate student, Brian Josephson, and also the work of Tony Leggett. And you will see how both these results and insights led to this year's Nobel Prize. Okay, so the key concept here is that of a junction. You may be familiar with the junction that's in your transistor in your phone right now. But this is basically 2 pieces of metal that are superimposed on each other, sometimes by evaporation, other times mechanically, and there's a thin layer of an insulator between them. Nothing particularly special. But when these 2 electrodes, these 2 pieces of metal go superconducting, then something strange happens. For now, let's just set aside this diagram. It's not more complicated than what you may have seen in high school or first year freshman physics. But Brian Josephson predicted theoretically that there would be a spike in the current voltage characteristics. Completely bizarre at the time. Nobody believed him. There's a famous story about him, the graduate student, getting in a fight with John Bardeen, the Nobel laureate, and eventually Brian turned out to be right. So this is the feature we are interested in. at this point and understanding how it relates to the work by Clark and Devoret and Martinez. Now, let me just walk you through, ignore the equation for the moment. It's an equation for this circuit. And let me just show you something that I'm sure you're familiar with, and that is the classical mechanical system of an oscillator. There's some damping, you could offset the angle, but I mean, by and large, we have intuition of how this system evolves in time, and that's the equation for the oscillator. And as you see, there's they do resemble. Let's not look into the math right now, but here's a dictionary of how you take a junction between two superconductors and look at its behavior and look at a classical oscillator, the spring or a pendulum. And there's a one-to-one correspondence between the angle or the time dependence of the angle, the voltage that you see across the junction. There is mass, and associated to that there is the capacitance. There's of course friction that is directly related to the resistance of the junction. So naively, or not so naively, we think we understand the pendulum. We should be able to understand what's happening with the Josephson junction. Now, what I want to show you here is that first, these junctions and the devices that they are connected to are big, relatively speaking. These are some of the prototype devices that involve Josephson junctions. SQUID doesn't stand for the animal; it stands for superconducting quantum interference devices. But this is from the 1980s, something similar. These are big circuits, and here is an image I got from John Kirtley, who's again a leader in this field of scanning SQUID microscopy, and he's showing the magnetic image of one of the components of this interference device. It's littered with scratches, with trapped external flux. So these are complicated things. Why on earth would they just behave like a simple oscillator, simple pendulum? And that got the attention of Tony Leggett and several others. And why is that? Well, as you may know, even one of the founders of quantum mechanics was troubled by the predictions of quantum mechanics and came up with this crazy idea of locking a cat inside a box, better be made of lead. And in that you have a radioactive source that may or may not decay. If it does, it's going to trigger an event, kills the cat. But until you open the box, you don't really know what's going on. So he said that if you take quantum mechanics seriously, the state of the cat is a mixture of living and dead cat. The English translation of his original article is available. You can take a look. Another leading figure in quantum mechanics asked, well, wait a second, at what point does the word and gets converted into or? Because right now, for a macroscopic object like me, there's no superposition. I'm standing here, I'm not standing at the same time between two places in this room. So something crazy has to happen between the microscopic and the macroscopic system. So people said, well, forget about this experiment. If you have a macroscopic system, it will always be in one or the other of the states, dead or alive, being here or somewhere else. Tony Leggett already on his way to his Nobel Prize started thinking about this, and he translated this question into something that can be modeled theoretically and characterized. So he asked the following: how much friction, how much dissipation do I have to introduce in the delicate quantum mechanical oscillations of a system to turn it into a classical system? Quantum mechanical systems tunnel. Quantum mechanical system can be coherently in multiple states. But when and how is this destroyed by the presence of dissipation, whether it's resistance in a circuit or friction in your pendulum? And in a landmark work, they actually realized that in a certain regime, despite the fact that the system of interest, such as this quantum interference device, despite the fact that it's a big system, there may be a regime where tunneling and even this delicate phenomenon of coherence may survive. And basically what Clark, Devore, and Martinez did is they said, okay, if Tony says so, let's see what happens. Tony is never wrong. And that's what happened. They actually did an experiment, careful experiment, to see whether the predictions are correct. I want to appeal to your intuition. So if you have a pendulum, you expect oscillations. If there is plenty of energy, you may see a full turn, right? But there's not much else going on. I mean, if your pendulum is somewhere here, this is the angle versus the energy of the system. It either oscillates here. If you provide some extra torque, eventually, your pendulum starts to go around and around and around. But there's no way that in this state, the pendulum just decides to do a spontaneous flip, classically. So we have continuous energy. Full rotations are not allowed unless you provide enough energy. In contrast, the quantum oscillator, the quantum pendulum, does completely different things. First of all, it has discrete energy levels. You cannot just set your oscillator or pendulum to be with whatever energy you decide it should have. There's a constraint on that, and also it could actually get out of this well, go from one state like this one, go all the way around, come back. Okay. In their experiment, John, Michel, and the other John made a very carefully assembled circuit where they protected this Josephson junction from thermal fluctuations. That was one of their worry, and various other electrical fluctuations in the circuit. And they actually demonstrated how the system can go from one discrete level to another. There's no continuous spectrum. So the bumps here correspond to those transitions that you see in the arrow. So if you choose an external radiation to have the right energy, you could see these transitions in the experiment. There's no way you could see this in a classical oscillator. The other landmark measurement was they measured the escape rate, as a function of temperature. Of course, if you have higher temperature, thermal fluctuations may allow your oscillator, your pendulum to go around. But at low enough temperatures, it should not happen. This straight line is what classical mechanics predicts. And right here, they observed that this big centimeter-sized circuit with the Josephson junction exhibits quantum tunneling. They call it macroscopic because it's the voltage they measure is a macroscopic variable. Next came by next I mean it took like 15 years to get here, but there were several other measurements that actually did or reconstructed something like the Schrödinger cat experiment. That they showed that this macroscopic object, like an interference device or the Josephson junction, can be in two quantum mechanical states coherently superimposed on each other. So there were two competing groups. The papers came out fairly close to each other. What they have done is they set up the system so that there are, these are discrete levels, but they are levels that are fairly close to each other. And if you have this double well system and you tune it properly, this is the tuning parameter right here, the tilt. You can match these energy levels from one well or the other, that is current going clockwise or counterclockwise. If you have quantum mechanical behavior and coherence, very important, coherence, very delicate phenomenon, then if you measure the energies here, they should do what is called an anti-crossing. These dotted lines would correspond to the absence of coherence, and what you expect from coherence is the full line. And this is what the experiment shows, that in fact there is coherence. There is something like dead and alive cat, well, it's not quite a cat, it's current state, in a macroscopic circuit. Why is this important? Michel Devoret and John Martinez and John Clark took this much further by making what is called a Cooper pair box. The structure may look complicated, but it's not a lot more complicated. Instead of one junction, you have two. Here, they introduced another energy scale to keep down charge fluctuation. That's called the charging energy. And eventually, they came up with what you could call an artificial atom. With discrete levels, you could manipulate the parameters of this atom. In contrast to hydrogen, you're set. There's nothing to manipulate there. Came up with this idea of transmon. If you take a look at what Amazon and Google and IBM are doing in quantum computing, they are using basically these results here. Microsoft is doing something else, but it still involves superconductors. Okay. What happened to Brian Josephson's idea of Josephson junctions? Well, what happened is that people started to make superconducting electronic logic devices to be able to interface with a quantum computer. And I just went to a conference in Santa Fe not long ago. A million used to be the number of junctions in a typical device. Now is being pushed much further to even higher numbers. Extraordinary the complex system. And again, it's all due to the work of Josephson and several others, but then Clark, Devoret, and Martinez. Okay, here's what I found. There's a very well-known blogger. Some of you may have listened to her podcasts, and she had a short video on this year's Nobel Prize, and literally she's asking, so one, who cares, and why was it awarded? For a variety of reasons. And it's interesting, I mean, with an audience close to 2 million, it's important to make sure you get right what you say. Basically, the idea of the importance of this discovery is being disputed by her and some of the others in the field. I hope I could convince you that this was a landmark discovery that's going to affect the evolution of computing and quantum computing right away. Okay, so my answer to her question, was it worth it? I think, yeah. Thank you.
All right. Well, thank you very much. Okay, so hi, everyone. Again, I'm Adam Jaffe, also a professor at Notre Dame, and I'm pretty excited to talk about the Chemistry Nobel Prize. So the awardees of the Nobel Prize were the three shown here: Richard Robson at the University of Melbourne, Omar Yagi, who's currently at UC Berkeley, and Susumu Kitagawa, who's at the University of Kyoto. And they're awarded for essentially developing and then understanding how to tune this class of compounds that are called metal organic frameworks. And so we'll talk about what that even means. But kind of a kind of zoom out of like why this is all important. It's important to recognize that the universe is made up of lots of different interactions between things. So these are either usually attractive or repulsive. Think of positive and negative charges attracting, gravity being us attracted to something that's much more massive. And so as a function of that, nature, if we can make it like a person, does not like a vacuum, because that makes it difficult to maximize, to increase the number of attractive interactions between things like atoms. And so we're very familiar with things like a very dense material, maybe a block of copper. So here's a block of copper, and if we heat it or put it under vacuum, nothing really much changes. This block stays more or less the same. We're also used to some compounds that I would call something like a molecular crystal. Imagine some particles, maybe they're like a millionth of a meter, a micron across, but certainly you could see it with the naked eye. You might have to squint. And they can pack together in various different ways, and maybe there's also some solvent in between them, something like water. An example could be we're used to seeing mud on the ground, but then when we heat that mud or pull vacuum on it, the water comes out, and then the mud cracks, right? Its pieces shrink to smaller pieces, because we've sucked out all of the solvent, and so we get this collapse, this densification of those particles. And so that's an example of a molecular, in that case that's not a crystal, but a real crystal you might have encountered is something like Epsom salt. We of course use it to make a nice bath, but it is some salt ions or atoms, and there are also some water molecules in between. But if you heat it up enough, that water comes out. But this year's Nobel Prize really gets at an interesting class of compounds that are porous. We're familiar with porous materials like a sponge, right? But a lot of the sponges you might have used, they come vacuum sealed in a really tight package and they're really small, and then they swell when they absorb water. But there are some solids that we can still imagine packing particles together, now shown by these little blocks, and maybe some solvent in between. But if we heat it or pull vacuum on it, we pull the solvent out and we leave behind these pores, these empty spaces. So at first that might be counterintuitive about how we achieve that, but through some precise chemical engineering, we can build these frameworks, these structures that are permanently porous. And that actually turns out to be really, really important. So there are a whole class of different porous compounds, and the way I'm classifying them in this plot is by how ordered they are. So if we think of a checkerboard, or maybe just sticking together marshmallows and toothpicks into a nice three-dimensional lattice, that's something that's very ordered. If we look at one spot in that crystal, it looks just the same as if we moved over to another spot. And so that's something with a high degree of order. And the metal organic frameworks, or MOFs, that I'll talk about today are pretty ordered. On the other hand, it is also possible to have sort of these jumbled up networks of things linked together. It might still be porous, and we could pull the solvent out and have that empty space, but it's less ordered. So what's really special about metal organic frameworks is how ordered they are, and them being really ordered makes it easier to figure out how all of the atoms and molecules are linked together, but also allows us to engineer their properties a lot more effectively than in the case of something that's disordered. So this concept of order arises in chemistry quite a bit. It also is sometimes termed more or less with this term crystallinity. And that's because a really ordered solid, where we've packed together all these atoms in a really regular way, is a crystal. And you've encountered crystals in your daily life. Here's some nice pictures of salt crystals. Here's another one that's certainly probably in all of your pockets, although we trim down this crystal of silicon and turn it into things like transistors that make our phones and computers work. But to make a crystal, what we have to do is get all of the atoms in the right place. And that's not so easy. We essentially have to have all of the atoms and molecules be able to wiggle around a lot until they find the exact right position that's the most stable. And so here I'm showing actually just water molecules, where here, at this kind of line moving downwards, here is liquid water, molecules all wiggling around. But then eventually, at this kind of interface, you can see they might rearrange a little bit, but they'd lock into place. And so here would be a crystal of ice. So the way that we form these crystals requires all this reversible moving around and bond making and breaking. And so that's where metal organic frameworks come in. They form in much the same way that that water formed into ice crystals on the previous slide. But instead, we're assembling this network using a metal node. So these are just metal atoms. We are familiar with many of these: copper, zinc. Many different metals across the periodic table can do this. And so each of those atoms is one node, and we can link them together in various different ways with organic molecules. What I mean by organic molecules are molecules that are mostly made out of carbon and hydrogen. So not just sort of the more simple definition of when you go to the store and you have your organic option or you have your option that's not organic. Here we're talking about just things made out of carbon and hydrogen. Things that are inorganic include metals, but it's essentially just everything else on the periodic table. And so that's why we classify metal organic frameworks as being organic inorganic materials, or hybrids. So they're this nice combination of metal nodes and organic linkers, and we may build up this nice framework. You can view this as a little snippet of the crystal structure. Of course, this is at the microscopic level. So the crystals on the previous slide, those are macroscopic objects, but if we zoomed in with a powerful enough microscope, this is how all of the atoms are arranged. The really nice thing about metal organic frameworks is that they are crystalline, which I already mentioned, but they're customizable, meaning we can choose so many different types of metal nodes and so many different types of organic linkers. And that can allow us to link these metal atoms and organic linkers in many different ways, in many different shapes. But also the metal nodes themselves and the organic linkers themselves can have different chemical properties. And that's really powerful. I'll give an example later on. So what did the Nobel Prize winners do? Well, Richard Robson is kind of viewed as the person who came up with the idea of viewing these networks as simply the nodes and the linkers, where it actually doesn't matter too much what they are. We could even just sort of break it down into balls and sticks, our marshmallows and toothpicks, if you will. But recognize the fact that if you have these nodes that can have different shapes to them, maybe sort of 4 directions coming out, 5, 6, whatever it is, and then link it together, you can form these whole networks. The structure of more dense solids, things like diamond, actually look a lot like this, but everything's all condensed and collapsed. There's no free space. But you could imagine expanding the distance between each of the little nodes. Everything about the shape at the atomic level looks the same, but you've just created these new cavities in your framework. Susumu Kitagawa then took that further and actually made quite a few examples of these porous solids, and was one of the first to actually show that you could do this, that you could take this framework made up of these metals and the linkers, and maybe you have some gas molecules in there, shown by these orange spheres, or maybe you have some solvent. He was one of the first to show that you could take those out and then remain with this porous solid, so you didn't collapse your sponge. They also showed that there's some flexibility there. So you can see here, this looks kind of more like a cube, and here it's sort of sheared and collapsed a little bit. It's sort of changed its shape. And so that's actually very interesting from a standpoint of how much or little gas or other solvent we could put in and out. And finally, Omar Yagi really grasped the concept that these are such customizable frameworks, and really showed that as a function of these different organic molecules that link together those metal nodes, we can get different sizes of the empty space in these frameworks, these yellow spheres kind of just representing that empty space, and also recognize that the nodes themselves where those metal atoms sit can have a lot of different shapes and sizes. Okay, so why does this all matter? The fact that we have these really ordered and very customizable frameworks. Well, I want to maybe tell you something that you might not know, that 10 to 15% of all of the energy that humans produce, so that's like 1/8 roughly of all the energy we produce, goes to separating things. This could be separating all the different parts of crude oil. This could be separating oxygen and nitrogen. This could be separating the precursors that we use to make polymers, which make up all the plastics that we use. But all of those separation processes take up so much energy that we produce. And so figuring out a way to do that more efficiently would be hugely beneficial to society. So this plot here is just showing, just for the United States, all of the energy we consume in a unit called quads. Don't worry about that, but it's a huge energy scale. But yeah, here's just showing that especially in this industrial sector, which takes up about 1/3 of all of the energy that we produce, now within that, quite a large amount of the energy that the industrial sector uses goes to these separations processes. And so those are all of those molecules and that I was speaking about trying to separate. For example, you might have even driven past some of these big plants and wondered, what are all those buildings doing? Why is there all these like gases and things coming off of it? So if you see a tower that looks like this is just a giant distillation column, actually very similar to the distillation columns that people would use to make, for instance, whiskey. But in this distillation column, we cool air down until it's a liquid, and air is mostly made up of nitrogen and oxygen. And this distillation column allows us to separate those two because they have slightly different boiling points. But it takes a lot of energy to cool air down to make it a liquid. And then we warm it back up again, so that's really inefficient. And we can only do it at huge scale like this. And so we would want better ways to do that. Just briefly, here are a few of the other separations that are really important to society. Things like different waxes, oxygen and nitrogen, certainly carbon oxides and methane from air, definitely other pollutants in the air, petroleum, and many others. But let's just zoom in on one specific example to really hammer home the idea of how important this is and how we can draw even inspiration from biology. The way that our body does this, our body has to do this separation too. We have to separate oxygen from air because we use oxygen in a lot of biological processes. So this big molecule that I'm showing here is hemoglobin. And so this is in all of your red blood cells. And what that hemoglobin is doing is it's pulling oxygen out of the air at this little site here. So this little blue molecule, that's oxygen. And it binds just to this little site. And when it does, it causes this big rearrangement of this molecule. But that's also fairly inefficient. But this molecule has evolved over millions and millions and millions of years to be really good at separating oxygen from air. So the idea that a lot of people have taken of metal organic frameworks is, can't we do something similar, but can't we make materials that are porous and can have very specific interactions with different molecules that we might want to separate, but we can design these metal organic frameworks exactly to do this one specific task. So here's an example of a metal organic framework where all these green spheres are iron atoms, the same type of atom that's sitting right here and that binds oxygen. But instead, see how many iron atoms there are in this sort of porous structure. So this is, again, a tiny snippet of the crystal structure. If we zoomed out, this would look like a powder sitting on our bench top or on our table. But it's capable of absorbing oxygen when the O2, now shown in red here, just binds to that iron center. And so this would be a way to grab oxygen out of the air and allow us to use it for medical purposes. It's actually used in making steel and a whole host of other technologies. And so ultimately, you can imagine using all of these concepts that the Nobel Prize winners did to play around with the nodes and putting all sorts of different metals there that can do different interactions with the molecules that we might want to separate, and also then connect them in different ways and have this huge amount of surface area as well. So it kind of blows my mind to think, but even in very small, maybe a gram or two of metal organic framework, you have a much, much higher surface area. Think about how much water fits into a sponge. Similar to this, we can fit lots and lots of gas molecules or other molecules we might want to capture or separate into a metal organic framework. So I think that hopefully shows how important metal organic frameworks can be for all of these separations processes, but also the storage of gas and many, many other applications. And so some of those are shown here, whether it's to create new ways to make fertilizers, whether it's ways to catalyze molecules breaking apart and pulling energy out of that, whether it's making more efficient emission of light, or even making cleaner drinking water, or even storing energy. We can actually use things like metal organic frameworks in a lot of those contexts. So I'll stop there, and I'll be happy to take any questions.
So we'll open it up for questions. Physics and chemistry. Go for it.
Let's see, should we stay up here? Or I guess that's best. Yeah, we'll stay up here. I'll go down here.
I have just to start off. So when you say quantum computing, can you explain that a little bit more? So what is happening in quantum computing? Is it a more powerful computing, smaller area?
It's not easy to explain right away, but I think there's a way. So if you think of how information is processed and is manipulated in a digital computer, the reason why it's called digital is because the computer works with bits, with zeros and ones. And there are well-known algorithms with which you could, transform, a number into zeros and ones, series of zeros and ones, and store information with zero being, your hard drive in one patch pointing down or pointing up. In a quantum mechanical system, rather than have 0 or 1, you can have two states, 0 and 1, combine them coherently. You could describe the state rather than 0 or 1 as basically a vector on a sphere, and you could manipulate. You could have tremendously more flexibility to encode the information in the first place. Then there are some tasks such as factorization, and factorization is known, according to the Shor's algorithm, to be much faster under the quantum computational framework. There are advantages for sure. One of the things that fascinates me in particular is that with a quantum computer you would be set to understand what a quantum mechanical system is doing. So rather than try and translate it into something that a digital computer understands, you could literally simulate what you want in the first place. That's kind of crazy. Yeah. So, yeah.
Thanks.
I have a question for Adam. First of all, thank you for the protein structure. I love that. So you described metal organic frameworks as one of the applications for them is for separation. Separation obviously very important, as you demonstrated. I did not realize how much energy was spent on just separating things from each other. But are there, I'm not aware of this, so it'd be nice to know, are there examples of metal organic frameworks that are used to make chemical reactions go faster? So like catalysis, like making catalysts, or making them more efficient. Could you expand on that?
Absolutely. Yeah, so to repeat the question, it's sort of, in addition to separations, which is definitely one application of metal organic frameworks, can we use metal organic frameworks to perhaps interact with chemical molecules to accelerate their reactivity, maybe to make them break apart or join together faster? And the answer is yes. So there's a lot of research using metal organic frameworks and with maybe specific metals or molecules, linking them together that would allow us to more easily join together molecules or break them apart. And especially at the academic setting, people are using all sorts of different combinations of metals and organic linkers and trying to, some of the most important catalytic reactions out there, I would say, are, here's another statistic for you, something like 3% of the energy we produce goes into making fertilizer. So it's something called the Haber-Bosch process, which is converting nitrogen to ammonia, which is then the base of fertilizer. And that's probably why we have about 8 billion people on the planet instead of 1 billion, is that we're able to make fertilizer. So not only is that hugely important for feeding the planet, but it also uses a lot of energy to convert nitrogen to ammonia. And so metal organic frameworks could be one way that you could then design a much lower energy, lower cost way to do that conversion. As we do it currently, we use sort of a mixture of iron and ruthenium, and we heat it way up and put it under a lot of pressure to do that conversion. And so finding a better way would be great. Commercially, I would say metal organic frameworks are not, to my knowledge, used to do this catalysis just yet. They haven't been around actually in the broad scheme of things all that long. And one of the downsides, I think it's important to talk about, okay, what are the limitations? Is it just a miracle material? No. Some metal organic frameworks are not the most stable. So if they fall apart, then you kind of lose a lot of these favorable properties that you might have. And so that's one of the key issues that people are trying to solve, is how do you have all of these really wonderful properties but not have the material fall apart, especially if you're using it over and over again. Yeah, hopefully that answered your question a little bit.
I have a follow-up question about manufacturing. So, are there like I guess could you go a little bit more into like limitations? Would it be like certain elements mixing together, like bond tables? Or are there like limitations or like different kinds of bonds that they can form with each other? How does that all play in?
Absolutely. So the question is, other than maybe perhaps also stability, what other limitations are there, or what kind of dictates, what tells us how to make these frameworks and how do they kind of put together and fall apart? And so such a really great question. It was also asking about, how do these bonds actually form and what can you do to change those? Yeah, so there's a lot of knowledge associated, chemists for centuries have really built up this body of knowledge about how metals behave and bond with other molecules. Even like you're alluding to, like how many molecules can you pack around one metal, and do there have to be certain angles that they form around the metal, or is it just unlimited? The answer is it's definitely limited. And then also when designing these organic molecules, you have to essentially think of it as like they have to have some sort of arm that can grab onto the metals, but then also how does how does the body of the molecule also behave? So that's a really insightful question, and yeah, that's something that people designing metal organic frameworks really have to think about how do these metals interact with these molecules, and do they form the framework that we might want to form? But we have a lot of the ability to do prediction then, because we have all this body of knowledge of how this framework would form. One other kind of limitation that I would also say is that there might be some metals, organic molecules, that have really wonderful properties that we think, oh, let's make a metal organic framework out of that. But we also have to realize that if this thing is going to solve some important world problem and we have to make a lot of this metal organic framework, well, we probably can't make that metal organic framework out of like platinum or some really, really expensive metal. So kind of balancing the chemical properties but also the real world applicability is really important to think about.
Another question. So with the people who won the physics prize, when did they do their core work? Like, what decade are we?
I should have mentioned that. So that was 1985. So it was about, oops, sorry.
Just cut now.
Okay. Is it better now? Okay. So, the prize for the technology for the junction and the theory was given 73. In the 60s, people started developing junctions. I think the original paper is 62. By the time the 70s rolled in, early 80s, it was a very mature system. By that time, it was clear to some that these circuits behave as if they are macroscopic quantum mechanical. But nobody. Tom Leggett was saying that somebody tried the same experiment as John Martinez and Clark and Devoret like 15 years before. It looked like they got the same result. Turned out that it has a classical explanation. So people have been going around this issue, but it was 85. Then in 2000 came quantum coherence, and then 2015 onwards, there's a big development of quantum computing based on these circuits. So yeah, it was 10 years ago already.
Yeah, so for both of these projects, has it taken 40, 50 years for this work to sort of become recognized as to how valuable it is? Because when was the chemistry work?
I would say most of the early work of Robson and then Kitagawa and Yagi showing that metal organic frameworks could even exist in their current form probably happened in late 90s, early 2000s, so actually not too long. I would also argue, though, that while we see all of this potential, there are only a few commercial metal organic frameworks, and so I think my interpretation then of the Nobel Prize being awarded to these people is essentially seeing the really, really great potential. And so, yes, it can really benefit humanity, and I think it's a little bit forward-looking. But yeah, actually, in the context of Nobel Prizes, I guess I don't have the numbers in front of me, but it seems a relatively quick turnaround for discovery to awarding the prize.
Whereas the physics one is more in use now.
Speaking of, is this better now? No. Okay, let me just stay with the big old mic here. In terms of turnarounds, one of the awards that I listed probably holds the record in 1987. The high temperature superconductivity, I think the paper was submitted December of when they actually bought their ticket to Stockholm soon after that. When I was in grad school, and I'm sure Adam would say it was during the dinosaur age, but then macroscopic quantum tunneling seemed to be accepted by most. Macroscopic quantum coherence, I was told by some of the leaders of the field that it's fiction, and it's an amazing turnaround now. Right? So it's hilarious to read some of the comments, printed comments on the Nobel Prize winning paper. There's somebody who claimed that, well, you guys don't know how to control the temperature. Your curve demonstrating quantum tunneling is just classical plus 15 millikelvin. 15 millikelvin seems tiny, but at that scale, it would have been a big deal. And Devoret and John Clark and John Martinez show that is a good old-fashioned, data analysis, putting all the error bars in, shows you that there's no way classical mechanics explains the data. Yeah.
Question to both of you. In your entire career, has there been a particular favorable invention that you prefer? Like it's top notch and that's really compared?
Tell me, so is there a favorable invention?
it's just like nothing else really compared to all the years that you've been in this.
My goodness, that's a loaded question.
Is the question of something that we've invented or something that we've just seen invented?
That's easy to answer.
Okay, yeah.
I haven't invented much. I have 2 patents, completely useless. Did you record that? Okay, probably. It's not easy to answer, but maybe I would say, what fascinates me right now, and maybe a year from now we'd have a different opinion, but this flux logic devices that we started working on and got dragged into is absolutely fascinating. It was inspired by Jurelson and his junctions by 3 Russian colleagues who came in the early 90s in upstate New York, Likharev, for example, State University of New York. So they figured out a way to process and manipulate data and information at very low energy cost. And that's the reason why some of these devices are so popular. Now, why do I mention that? If you take a look at what's happening with all the data centers and how they're building a modular nuclear reactor next to it, the data processing comes at tremendous energy cost, and these things may be useful at some point.
I have a question.
Yeah.
This innovation process, they're turning software data into physical liquid?
Oh, no. Sorry, I apologize. There are way too many jargons I'm throwing out. But it's a way of computing with objects or states of the circuits that I just described, right? So let me try it again. So let's assume that 0 would be current going around the loop in one way, and 1 would be going the other way, right? If there are ways to add zeros and ones, in a way that makes sense with logic gates, then suddenly you could actually have a computer. It's classical. This is classical. This would be just interfacing with a quantum device. Adam, good luck to you.
Yeah, well, that's such a good question. Well, I think what gets me into science is how many cool discoveries there are. To pick one is really tricky. I think one that came to mind when you asked the question was LEDs, light-emitting diodes. I wouldn't say it's necessarily just one discovery that's happened in the past 10, 15 years. The concept has been around longer than that. But if I just think back about, how much like our phone technology, how much lighting in the room, how much TVs, that kind of thing have come along, and that's enabled by light-emitting diodes, so this kind of new, more efficient way of emitting light. So we're familiar with the old-time incandescent bulbs. It's just got a filament in it, and you just pass current through it, and it heats up and gives off light, right? An LED is a fundamentally different technology, and what I think I like about it as a chemist is that the materials at the core of it can be a lot of different things, and that makes us able to use those different materials for different specific applications. So you might hear OLED. O stands for organic, and so that's using some of those carbon and hydrogen-based molecules, and that allows you to even have flexible displays. But then actually last year's Nobel Prize was for something called quantum dots, or very, really small particles, and they're so small that they have some of this, non-classical or quantum behavior that allows the color of light that they give off to be changed just based on their size. And people use those now in TV displays. So if you ever see QLED, that's quantum dots. So all these different LED technologies, but enabled by cool to me, cool. Chemistry, I don't know, I think it's pretty amazing. Like if, I watched like Star Trek and whatever growing up, and you see all these displays and it just looks magical, at least it looked magical to me. Then like imagine having a paper with all of these like moving displays on it, and now we kind of have that now, which is pretty wild.
Yeah.
I'm very thankful and hopefully trusting the truth.
Thanks, and thanks for your great question.
All right, so let's see, I think my microphone has died as well. So thank you so much for coming out tonight. On December 2nd, we have our next Our Universe Revealed talk. This will be Jonathan Crass, and he will be talking about exoplanets. He's an instrumental scientist.